Greetings all. Today I want to go over the code a little bit on operating the HP dot matrix 4-character display. See my previous videos for more information on this. But to go over the code a little bit, first thing I do, of course, we declare some various variables. For the HP display, I've got data in this low and high nibble. Those will be used for capturing the data to display and then splitting it up into most significant and least significant nibbles. I've got a bit buffer down here, bits 0 through bit 6. This is the 7 bits that will be shifted into the display to fill each column, one column at a time. And then up here we've got some delay and some other various variables that will be used throughout the program. The digit 1, 2, 3, and 4 address, those are going to hold the column address of each digit in the HP display, and this will be seen a little bit more later on in the discussion here. So we declare the variables, and once we get them declared, then I initialize them. And in this case, excuse me, in this case, I basically just clear every one of them. We start out with all of them at 0. And then we set up the ports for display. I'm using port D for the HP display. Bit 0 is the clock. 1 is the data that's going to be displayed. This is basically the shift register input pin. Bit 2 is a blanking output. This turns off the display so that shifting data in does not display sporadically. And then bits 3 through 7 are the column 1, 2, 3, 4, and 5 outputs. Once the data is shifted into the shift register for a given column, then that column's output is taken high to display that data. TPA and TPB are timing pulses from the 1802 that will be watched and used to capture the various data to display. Down here are some other variables that will be initialized, and again, these are basically just cleared, so everything starts out at 0. So here we watch for timing pulse A. So what I do is I check port E, bit 0. I sit and watch that, and until it goes high, this thing just sits in cycles. Once it goes high, it goes down here to latch, and it looks at port C to get the various data. This is the address data here. It gets the address data. It puts it into these variables. Low nibble high, the high nibble high, the low nibble low, and the high nibble low. This gives me 4-bit nibbles from a 16-bit address. Each of those 4-bit nibbles then will be displayed on the display. TPB down here, this is watched, and this captures the data that will be displayed. So we have 2 bytes of address and 1 byte of data that's going to ultimately be displayed. Now, since the L2 computer only has 256 bytes of memory. 1 byte of address is all we need, so that's all I display. But this could be expanded to display all 16 bits if needed. And then this latch low, once it reads the address, then it comes down and it reads the data on port B. And again, it separates the high nibble from the low nibble. And those are stored in the high and low nibble high variables. That is just the repeat of the TPA routine that we've already seen. I guess I've got extra copies in here for some reason. Okay, so here we come to the function or the subroutine that operates on the display. So what we do first is we turn on the blanking input, and again, this keeps any data that's shifted in from sporadically showing on any of the LEDs in the display. And we start out, when the way this display is set up, you shift in 28 bits. The first 7 that you shift in will be displayed in the rightmost digit, which is digit 4. The next 7 will be in the third, which is digit 3, and then the next 7 in digit 2, and the last 7 in digit 1. All of those are shifted in. So we take the low nibble that we took from the address, or the data, and we go to lookup table. Now the lookup table is right here. And this takes a nibble that is from 0 through F. And when we jump to this lookup table, the address of the lookup table is in the program counter. The data that is in the variable then is added to the program counter. And that gives us an index into this lookup table. So let's say, for instance, we want to display a 4. So we go 0, 1, 2, 3, 4. That gives us the value of hex 14. So take that value, and then we return from the lookup table with a value of 14 hex in the W register. Then we call get EE data. And what that does is that takes us to this. That takes us to this table, which is in the EEPROM. And if we go to address 14, that is 0, 1, 2, 3, 4. That's right here. Now, the way this is set up is this is the column data to display a given hex character, and it's in 5 consecutive columns. So this 3E, 45, 49, 51, 3E, those 5 bytes display the character 0. The next 5 display the character 1. The next 5 display the character 2. The next 5, character 3. And then at 14, we start with the character the data for 4. So 0C, 14, 24, 7F, and 04 when those are put into columns 1, 2, 3, 4, and 5 of a given digit on the display, it will display a 4, the number 4. And it works that way for any of the hex characters. So we get that first byte, and then we set up a counter because we're going to be counting 7 bits, and we move that into the file select register. Then we call a routine called bitsep. And bitsep okay, where is it? Bitsep is right here. So what we do is we go through each of the bits. We look at the first bit 0 of temp1 variable, which is what we put that data in. We check and see if it's a 1 or a 0. If it's a 1, we go here and we go down to 1, 2, 3, 4. We go down to here and we set that bit, rotate it into the temp file, and then shift it into the shift register of the display. Then we come back up here. We rotate that right here, and we come back up and we check the bit 0 again, which is now has the data from the previous place shifted into it. This way we can shift in whether it's a 1 or a 0 into the shift register. Once we do that, we return and come back up here again, and then we call up the EE address. We go to the variable or the address for that digit, and then we call the shift out routine, which then shifts out all those bits into the shift register. And we do that 7 times. And then we come back and we do the same thing for digit 3, and then digit 2, and then digit 1. And then at the end of that, we take column 1 bit high, and we display that for, in my case, it's 10 milliseconds. In this case, we display, or 150 milliseconds. So we display that for 150 milliseconds, and then we turn that off, and we do the same thing, but we load for column 2. That's down here, of course. And then at the end of column 2, we take column 2, enable high, display it for 150 milliseconds, or some number of milliseconds. Take it low, go to column 3, do the same, column 4, do the same, column 5. Now, if we do this in rapid succession, it looks as though all of the columns are on simultaneously, but they're not actually. Of course, they're multiplexed. And then once we get through once we display all that data, then we go back to the beginning and we do it all over again. We check to see if the address or the data from the 1802 has changed. If it has, we it downloads the data. It rechecks the address bus and the data bus, and it captures the current value on each of those two buses, and then it goes through and displays it as we've discussed here. If the data has changed, of course, there'll be new data on the display. If it's the same, it'll show the same. And I can show you that a little bit on my development board here. If I turn this on, now I've got this set up. I don't have it set up to the 1802 anymore. And the way the camera interacts, it's not very easily done. But you can see that on the LCD and the LED display showing the same data, but due to the speed of the camera and such, it makes it look weird. So it's kind of difficult to see. But on my previous videos regarding the ELF2 and this HP display, it shows them operating just fine. So anyway, that's the code. If there's any questions or comments, be sure you add your comments. I read all the comments. If there's something else that needs explained, or if somebody wants a copy of the code, just let me know and I'll try to get it to you. But until the next time, I think that's it for now, and adios. Thank you.